All right, lesson 9-4. Need homework on page 737 out. There are the answers there, and you're writing the sample space, so you should have listed them all out there somehow. An easy way just to double check yourself is to count them. Like in number 1, you need to have 10 answers wrote down. Okay, 12 down here. Just count them all out. Down at the bottom, page 738. Okay, the lesson is we're going to start on page 742. I'm skipping the random number generator on the calculator. We're going to go right to 742. A simulation is an experiment that is designed to model the action in a given situation. So for example, you use a random number. We're not doing that. We're not going to use that part. Simulations often use models to act out an event that would be impractical to perform. So for example, if 2 teams were going to play a football game or something, and it rained, and they couldn't play, and they may have decided just to toss a coin to see who would win. That's a simulation. It's doing something in place of the actual event. So I always give the example, like if you've ever been to like an amusement park or something like that. They have you sit in like an airplane simulator or a rocket ship simulator. You're sitting in the rocket ship simulator. The seat starts to move and it starts to vibrate and it makes all this kind of noise. And sometimes they put scent in the air to make you feel like you are really flying in a rocket ship. That's a simulator. You're not really in a rocket ship. So that's the same type of thing here in math. You're doing something in place of doing something else to make it seem like it's the same thing. Okay, so for number 1 here. A cereal company is placing one of 8 different trading cards in its boxes of cereal. If each card is equally likely to appear in a box, describe a model that could be used. So 8, 1 of 8. Think about what we've done before with 8 outcomes. We've tossed 3 coins. There are the outcomes of the coins. So you could simulate 3 coins in places of making a simulation for 8 different trading cards. So toss the 3 coins. If you get a tails, tails, heads, you get card number 6. If you get a heads, tails, heads, you get card number 3. That's just an example. So letter A here. A restaurant is giving away one of 5 different toys. 5, okay? If the toys are given out randomly, describe a model that could be used to simulate which toys would be given out with 6 different meals. So 5 toys. So not a lot of things that we've done come out to 5. I think about rolling a number cube. Those are usually 6. I think about coins. If we have 1 coin, that's 2 outcomes. If we have 2 coins, that's 4 outcomes. If we have 3 coins, that's 8, not 5. We need something with 5. So maybe we're going to put numbers in a hat. 1, 2, 3, 4, and 5. And you close your eyes and you take a number out of a hat. Now this is talking about 6 different children's meals. So you have to draw a number out of the hat 6 times. You have 5 cards in a bag, numbered 1, 2, 3, 4, 5. You draw one out, you replace it. It's important that you say that part because you have to put that back in the bag and you do that 6 times. That could be a simulator for this example. Number 2, every student who volunteers at the concession stand during a basketball game will receive a free school t-shirt. The t-shirts come in 3 different designs. Design a simulation that could be used to model this situation. Use your simulation to find out how many times a student must volunteer in order to get all 3 t-shirts. So in this one, they're saying you have a spinner with 3 equal sections. And you assign one of the sections to a different color shirt. And based on the simulation, a student should volunteer 4 times to get all 3 shirts. No, you would, that would just be this example, this experiment. You would say you would have to spin the spinners until all 3 colors were chosen. So here we had a blue and a yellow, and we had another blue. So we had to keep going. It could have stopped with 3. It could go on to 100, who knows? But what you say is you have to spin it until all 3 colors were chosen. Okay, part B. Mr. Chen must wear a dress shirt and a tie to work. Each day he picks one of his 6 ties. Design a simulation that could be used to model this situation. Use your simulation to find out how many days he must work in order to wear all of his ties. So go ahead, and we have 6. So think of something that we've used that represents 6 outcomes. Pause and go ahead and try that one. Okay, for this one, 6 outcomes. It's a number cube. That one usually is very easy. Could you set a spinner with 6 equal sections? Yes. Could you set 6 different numbered cards in a hat? Yes, that would work too. But if it's 6, lots of times that's a number cube. So a number cube, you toss a number cube until all 6 numbers have been rolled. I'll show you what the answer book even wrote here. You roll a number cube. Each number represents a different tie. Repeat the simulation until all the ties are selected. Okay. So you can do the simulations even if they don't have an equally likely chance to be chosen. So for example here, number 3. There's a 60% chance of rain for the next 2 days. Describe a method you could use to find the experimental probability of having it rain on both of the next 2 days. So 60%, maybe we're going to say 3 red and 2 blue marbles in a bag. That equals 60%. Because if there were 6 red and 4 blue, that's 6 out of 10. That's your 60%. So they're just saying 3 red and 2 blue, same thing, 60%. So if 60% of them represent the rain, then the red means rain. And this means no rain. So you randomly pick one marble to simulate the first day, and you put it back, and then you pick out another marble for the second day. That's just one example. You could have done a spinner with 60% says rain and 40% says no rain. You could have did something like that. You could have put 6 cards in a hat that said rain, 4 cards in a hat that said no rain. Could have did something like that. Lots of different examples. So for letter C here, during the regular season, Jason made 80% of his free throws. Describe an experiment to find the experimental probability of him making his next 2. So pause the video and write something down for that. Okay, so we need something with 80% that he makes. So maybe you made a spinner with 80% saying he made it, and 20% said he missed, didn't make it. And maybe you could have said 4 marbles in a bag that were blue, and the blue means he made it. And 1 red and said he didn't make it. Cards in a hat. As long as you're showing, though, you can show 80% somewhere that he made it, because he made his free throws. And then, oh, one more thing that I should have told you. Let me get back to that. Whoops. You have to say he does it 2 times, because they're talking about the next 2 free throws. So you can say they spin the spinner 2 times. They draw a marble out of the bag and they put it back in, and they draw another marble out of the bag. So we have some guided practice there, just 2 problems. Go ahead and try those. Pause the video. Okay, for number 1, they have waffle cones and sugar cones. So we're talking about 2 things. So something very easy is tossing a coin. Tails means waffle, and heads means sugar. And how many times would you have to do that in order to get both cones? You don't know. As many times as you need to get a tails and a heads. There's not a numerical answer. Okay? Number 2. Electronics store has determined that 45% of its customers buy widescreen TVs. Describe a model that you could use to find the experimental probability that the next 3 TVs they're going to buy are widescreen. So we need something with 45%. So maybe you're saying 45 cards in a hat that say widescreen on them, and 55 that say not widescreen. You could do a spinner with 45% widescreen and the other 55% not. And then they're talking about the next 3 buyers. So whatever it is that you pick, that's 45% and 55%, you would say you would have to do that experiment 3 more times. All right, so page 745 and 746. And that is it for lesson 9.4. Make sure if you're doing 745 here, don't do a spinner every time, or don't do a cards in a hat every time. Change it up a little bit. Do something different. Okay. All right. Have a good day, everybody.